So how can we rationalize the different reactivities of the different carboxylic acid derivatives? Well, the more basic the Z group, so whatever that Z group is, that means that if the Z group is more basic, that means it is it's more likely to grab a proton. That would mean it's more likely to donate electrons, right? So if it's a more basic Z group, it means that Z would donate the electron density to the carbonyl carbon to a greater extent. So essentially, the Z group would be lending some of its electron density to that carbonyl carbon if it is more basic. So what that really means is that the more basic the Z group is, that makes the carbonyl carbon less partially positive. So let's think about that a little bit with these two carbonyl derivatives. So we have the acid chloride and the amide. And neither of these carboxylic acid derivatives can be fully described by this one structure. Sure, this is the highest contributor of all of the different structures we would use, but we would need all the different resonance structures to fully understand how these molecules react and what their full nature is. Maybe we'll say, just for argument's sake, that this is the best resonance structure, so it's 60% of their character. This would probably be a good time for you guys to write up 2 more resonance structures for each of these. So this one's going to have 2 more, this one's going to have 2 more, and then think about which ones would be the better or worse resonance structures, or the more or less contributing forms. So you've done that, now you're back. Well, the oxygen is more electronegative than that carbon, so one thing that that we could show for both of these is the oxygen pulling electron density up to itself to show a second resonance structure where we have a negative charge there and a positive charge there. So we'll show that with both of them. A third resonance structure that we could show is both of these, this NH2, this Cl, have electrons, and they can donate those to that positive charge. So the third resonance structure would be shown here. So when we think about this resonance structure versus this resonance structure, which of these would be a more stable form, right? Do we want to have the positive charge on the chlorine or the positive charge on the nitrogen? Well, we know chlorine really does not want to be positively charged. It's really stable as a negative charge. We know that because HCl is a really strong acid. That tells us that Cl- is really stable. NH2- is not as stable. NH3 is a really weak acid, which tells us that negative charge on nitrogen is not as stable. We've seen nitrogen be positively charged in a stable form throughout much of our chemistry study. So this is a really stable positive charge, whereas this is a really unstable positive charge. So if this is 60% of the resonance forms, this might be 10%, while this is 30%. That would kind of mean that these take on the rest, so that's 10%. We'll say that this is 30% of the resonance form. This is 10% of the resonance form. So essentially, which group is more basic, NH2 or Cl? Which is more likely to give up its lone pair of electrons? NH2 is much more likely to donate those electrons. It's the more basic Z group. So this, if we show the hybrid of all 3 of these, the partial positive of the amide is going to be really small. So for these 3, we have a small partial positive on the carbonyl carbon, because the nitrogen is willing to give up its lone pair of electrons. Whereas with the acid chloride, the chlorine does not want to give up its lone pair. So that means that the partial positive on that carbon is substantially larger. So the more basic the Z group, so the nitrogen is a lot more basic, that makes the carbonyl carbon less partially positive, which means it's less electrophilic. So less electrophilic. Because a larger positive charge means it's more electrophilic. So that's one way of thinking about why different carbonyl derivatives are more or less electrophilic. But the book and I like to kind of talk about multiple ways that we can rationalize this. So we're going to move on to the second way right now. The second way I usually talk about the electrophilicity of any of the carboxylic acid derivatives is based on the basicity of the Z group and how that relates to its leaving group ability. So if it's a good or a bad leaving group. And we kind of put these things into two categories, like we're talking about things in a different way, but really we're still talking about things in the same way. Is this Z group basic or not basic? And we can relate the stability of the leaving group to the pKa of the conjugate acids. And that will tell us how stable that leaving group is by itself, so how good it is as a leaving group. And remember that strong acids have stable, weak, stable, weak. Strong acids have stable, weak conjugate bases. Okay, so how does that relate to all of these? So what are we doing with this nucleophilic acyl substitution? We're treating these different functional groups with a nucleophile that adds to the carbonyl carbon, and we have our substituted product with the nucleophile on there. What else is in each of these, though, is the leaving group. So acid chloride gives us Cl- as the leaving group. The anhydride gives us the carboxylate as the leaving group. The ester gives us OCH3- as the leaving group. The carboxylic acid gives us OH- as our leaving group, and the amide would give us NH2- as our leaving group. So the better the leaving group, the more reactive the species is going to be. So the more electrophilic the species is going to be. So what are the conjugate acids of these? We just add an H to all of these, so HCl, acetic acid, methanol, water, and NH3, ammonia. So again, which of these is the best leaving group? Well, the strongest conjugate acid would give us the best, would relate to the best, most stable leaving group. So HCl has a pKa of -7, super strong acid, great leaving group. Acetic acid has a pKa of 5, still a pretty good acid, pretty good leaving group. Methanol has a pKa of around 16, a lot worse of a leaving group compared to the carboxylate. Water, 15.7. So really pretty much the same thing as the ester. And then ammonia is 38. So that tells us that this is significantly, super substantially the worst leaving group, and Cl- would be the best leaving group. So what that tells us is that as far as electrophilicity goes, as rating these in reactivity, this is going to be by far the strongest electrophile, the most reactive species, and this is going to be the weakest electrophile. So the E+ ability increases in that direction. So hopefully that made sense. Yeah.